Quantum computing, hype versus reality. Quantum computing has garnered enormous public attention, with media headlines and stock markets often portraying it as an imminent revolution. In reality, experts emphasize that the technology is still in a very early, noisy, intermediate-scale quantum NISQ stage. Today's quantum processors have only tens to a few hundred qubits, each suffering from short coherence times and error rates on the order of 0.11%. Qubits must be operated at cryogenic temperatures and are extremely sensitive to noise and decoherence. For example, recent work at Aalto University achieved a millisecond-scale coherence time for a superconducting transmon qubit, a record. But even millisecond coherence only allows thousands of gate operations before errors accumulate. In practice, current machines can run only very shallow circuits, hundreds to thousands of gates, before noise overwhelms the result. Scaling to large, fault-tolerant quantum computers faces daunting barriers. Error rates and error correction. Every physical qubit must be redundantly encoded into many physical qubits to correct errors. Even with cutting-edge codes, overhead is immense. IBM's researchers note their new quantum LDPC code uses 288 physical qubits, data plus syndrome, to encode just 12 logical qubits, 10x fewer qubits than surface codes, yet still hundreds of physical qubits per few logical qubits. Microsoft's topological qubit plan likewise assumes an error rate goal of 10 circumflex 4 per physical qubit. With 1,000 physical qubits per logical qubit, roughly 1 million physical qubits would be needed to get approximately 1,000 logical qubits. In other words, reaching even modestly useful logical qubit numbers likely requires on the order of 10 circumflex 5, 10 circumflex 6 physical qubits, far beyond today's approximately 100-500. Decoherence and noise. Real qubits lose their quantum states quickly. As one ORNL expert explains, current devices incur 1% error per gate, so after approximately 10,000 gates, the accumulated errors make results useless. He notes we must push error rates below 0.1% to run lengthy algorithms. Similarly, Google has demonstrated that increasing error-correcting code distance reduces error per logical qubit, but we are still inches up on the point where a quantum computer can outperform classical ones. Control and hardware scaling. Building large quantum hardware is technically complex. Superconducting qubit chips must be wire-bonded or bonded with control electronics, all cooled to millikelvin temperatures. Crosstalk between qubits, calibration of thousands of microwave or laser control lines, and intricate cryogenic engineering are formidable. Different technologies, superconducting, trapped ions, etc., each have trade-offs in fidelity, speed, and scalability. Industry roadmaps, discussed below, talk about modular architectures, stitching together many chips via cryogenic links or photonics, precisely because a single monolithic chip can't feasibly reach millions of qubits. In short, none of the competing approaches have a clear path to becoming reliable, fast, and small enough to tackle the much-hyped applications. In summary, the technical limitations are profound. Qubit instability, noise decoherence, high gate error rates, and the enormous overhead of error correction make truly large quantum computers years, if not decades, away. Current NISQ processors can explore proof-of-principle algorithms on tiny problems, but they cannot yet run the deep circuits needed for most useful applications. IBM.com or NL.gov. Quantum computing today is not a drop-in replacement for classical machines, and overcoming these scaling barriers is the central focus of the field. Hype versus reality. Media and investor claims. Public and investor hype around quantum computing has been extremely high. Media headlines often trumpet quantum breakthroughs and announce that quantum machines will soon change everything. For example, Google's blog proclaimed in late 2024 that its 105-qubit Willow chip performed a benchmark in under 5 minutes that would take a supercomputer 10 circumflex 25 years, touting it as a major step toward practical quantum advantage. D-Wave's February 2025 announcement claimed its annealer achieved quantum advantage on a materials simulation that supposedly would take classical supercomputers millennia. Each such announcement has driven surges in quantum-related stock prices and investor interest. However, these claims often elicit skepticism. Many announced quantum advantages turn out to be contrived benchmarks or specific tasks. In Google's 2019 Sycamore experiment, they ran a random circuit sampling that they estimated would take 10,000 years on a classical supercomputer. IBM quickly countered that a Summit supercomputer could do it in approximately 5 days with optimizations. Scott Aronson notes that despite the back and forth, Google's 53-qubit run still did require entire days of computer time, with the world's fastest supercomputer to replicate. This shows quantum supremacy was a milestone, beating classical on a contrived task. But it was also largely academic. It did not solve a practical problem. The pattern of hype and pushback has repeated. Syal Mam reports that almost every major quantum advantage claim, Google 2019, IBM 2023, D-Wave 2025, etc., was subsequently challenged by independent researchers using clever classical methods. As Giuseppe Carleo, EPFL, warns, journals and media often broadcast flashy results from corporate labs, but give slim to no coverage to the later refutations. For instance, NVIDIA CEO Jensen Huang caused a stir by saying useful quantum computers are 15-20 years away. Quantum companies pushed back, but many analysts privately agreed that practical devices will take decades to surpass classical machines. In short, media hype and investor enthusiasm far outpace current capabilities. As Nature columnist Joan Arrow observes, big quantum announcements often see results questioned within months and sometimes retracted. Industry roadmaps and expert commentary. Major quantum hardware players publicly share their long-term roadmaps, and all emphasize that fault-tolerant quantum computing is still years or decades away. Google, Alphabet, Google's quantum AI lab famously announced in 2019 that it had demonstrated quantum supremacy with 53 qubits. It quickly set an ambitious goal. Sundar Pichai pledged to build a useful, error-corrected quantum computer by 2029. Analysts interpret this as needing on the order of 1 million physical qubits to achieve enough logical qubits. Google's recent Willow chip, 105 qubits, incorporated better coherence and error mitigation techniques. Google's stated approach is multifold: steadily improve qubit fidelity, demonstrate error correction at small scale. It has shown small logical qubit demonstrations, and incrementally increase chip size. IBM has a well-documented public roadmap. In late 2022, it unveiled its 433-qubit Osprey processor, more than 3 times the previous 127-qubit Eagle chip. IBM touted this as a step closer to solving previously unsolvable problems. IBM's roadmap calls for 4,000 plus physical qubits by 2025 and a fault-tolerant system by 2029. In mid-2025, IBM announced building the world's first large-scale fault-tolerant quantum computer, Starling, in Poughkeepsie by 2029. Their timeline: deliver near-term quantum advantage by 2026, small non-error corrected gains. Then Starling, 200 logical qubits, 100 M-gate circuits. By 2029, IBM's leadership stresses incremental progress. Every year they raise qubit counts and modestly improve fidelity. As IBM VP Jay Gambetta put it, each roadmap step scales computation capacity and paves way for eventual fault tolerance. But importantly, IBM cautions these goals are aspirational and subject to change. Microsoft has pursued a very different approach. Topological qubits, built from Majorana zero modes, still theoretical until recently. In February 2025, Microsoft announced a breakthrough Majorana 1 processor and new material, a topper-conductor, that it claims can host stable topological qubits. They describe Majorana 1 as the world's first QPU, powered by a topological core, designed to scale to 1 million qubits on a single chip. Microsoft's roadmap, via DARPA's US2 QC program, aims to build a fault-tolerant prototype in years, not decades. Quantinuum, Honeywell Quantinuum, a spin-off of Honeywell's quantum program, recently published a detailed roadmap. It claims an accelerated hardware roadmap aiming to deliver a fully fault-tolerant universal quantum computer by the end of the decade, 2030. In addition to these corporate roadmaps, independent experts echo caution. ORNL and Brookings experts note that we should expect quantum advances to unfold slowly and incrementally, rather than in a sudden leap. As ORNL's Ryan Benink puts it, today's quantum computers are systems we experiment with that classical machines can still easily outperform on meaningful tasks. Executives like NVIDIA's Huang advise patience, 15-20 years to practical QC, while others warn of a possible quantum winter if hype-driven expectations collapse. For example, the QCI stock saga. In summary, official statements from IBM, Google, Microsoft, Quantinuum, etc. All project fault tolerance approximately 2030 and beyond, and many experts publicly and privately acknowledge that the big promises lie well into the future. Key milestones and community response. Over the past decade, several high-profile milestones have drawn attention and controversy. Google's 2019 quantum supremacy announcement, Sycamore chip, made global headlines for performing a sampling task in approximately 200 seconds that Google claimed would take 10,000 years on a supercomputer. The claim was significant. It was the first time a quantum device definitively outperformed a classical machine on any task. However, IBM and others immediately pointed out that a well-tuned classical algorithm could solve that particular problem in a couple of days, not millennia. The scientific community thus viewed the claim as both real, quantum did win, and limited, only for a contrived test, and classical computers fought back quickly. As Scott Aronson noted, supremacy is not a moon landing, something achieved once and forever. Classical methods will continue improving, so the quantum classical contest continues. Other notable events include demonstrations of small-scale quantum algorithms, for example, early quantum factoring of tiny numbers, proof-of-concept optimization problems, and achievements in error correction. For instance, Google and others have periodically reported improvements, increasing the distance of a surface code logical qubit to show error suppression, or running dozens of qubits with some error mitigation. In November 2024, Google's Willow benchmark, 105 qubits, set a new record in random circuit performance, again claiming an astronomical classical time equivalent. But each such record has been met with the same pattern: PR excitement followed by scrutiny. Moreover, quantum annealing vendors have their own milestone claims. In March 2025, D-Wave reported quantum advantage in simulating magnetic materials with its 5,000 qubit advantage 2 annealer. However, independent studies showed that classical algorithms could reproduce or even outperform those results in hours or days. This led to a vigorous public debate. D-Wave's CEO defended the work, but critics, often academic physicists, warned that the model of using high-profile publications to broadcast results is becoming more and more problematic applications, real potential versus classical domains. Quantum computing has well-identified potential in certain domains, but it will not be a universal substitute for classical computers. The clearest promise is in simulating quantum systems. Quantum algorithms, for example the variational quantum eigensolver, can in principle model molecules, materials, or chemical reactions more efficiently than classical computers. Quantinuum and others expect the first useful quantum applications to be in scientific discovery. Studying superconductors, magnetic materials, and complex molecules, Microsoft explicitly cites computational chemistry as a use case for its projected 1,000 logical qubit machine. Other algorithms offer more modest speedups. Grover's search gives a quadratic improvement for unstructured search problems, which might benefit some optimization or database tasks, but not enough to break current encryption or replace general computing. Shor's algorithm threatens public key cryptography, like RSA, but requires thousands of fault-tolerant qubits to factor large numbers, far beyond today's capability. Classical post-quantum cryptography is already being standardized, so quantum's cryptographic impact will not be immediate. where quantum is unlikely to replace classical computing, routine data processing, machine learning, web services, video, games, and general-purpose computing. Quantum computers are not faster at everyday tasks, or even many scientific tasks. They excel only at specific problems with the right mathematical structure. Even in AI or optimization, emerging quantum-inspired classical algorithms already draw ideas from quantum theory. Blurring the lines, experts expect a hybrid future. Classical HPC and specialized accelerators will handle most workloads, with quantum co-processors providing boosts for select problems. For now, all new quantum advances must pass the test of delivering a clear advantage over the best classical approach, which has proven elusive except in contrived benchmarks. Conclusion. In conclusion, quantum computing is partially overhyped in the popular imagination. The media and some corporate messaging often portray it as a near-term revolution, but the technical reality is that truly useful, error-corrected quantum computers remain a distant goal. Scaling up from today's noisy 5,400 qubits to millions of physical qubits for thousands of logical qubits will require solving fundamental problems in qubit design, materials, error correction, and architecture. Leading companies and experts agree on that point. IBM, Google, Microsoft, and others all forecast multi-year roadmaps culminating around 2030 or later for large-scale fault tolerance. Key milestones like Google's supremacy and D-Wave's annealing experiments are real achievements, but they have also repeatedly shown the gap between performance on special tests and solving practical problems. It is a legitimate field of research with demonstrated small-scale successes, and it holds promise for breakthroughs in chemistry, materials science, and optimization tasks that stump classical machines. But those breakthroughs will arrive only after a long series of engineering leaps. As one national lab researcher put it, today's quantum processors are tools for experimentation. A future quantum supercomputer will require an entirely new level of accuracy, reliability, and sustainability that we just haven't seen yet. The scientific community broadly agrees that we should temper immediate expectations, invest wisely, including in post-quantum cryptography and AI, and recognize that quantum's real impact lies in the long run, not the next quarter. Sources: authoritative reports from IBM, Google, Microsoft, Quantinuum, and independent analyses. Please like and subscribe for more mind-boggling videos.